So when it comes to reactions involving the types of compounds we've just been talking about, the electrolytes, whether strong or weak, as well as non-electrolytes, um, we need to look at how these perform in reactions. And when we talk about these types of reactions we can show in ionic equations. And these ionic equations can take three different forms: molecular, ionic, and net ionic. So we're going to start with the reaction of lead nitrate and potassium iodide. Now when these react, they form lead iodide and potassium nitrate. Now, as always, we should balance our equation, and we can do that by placing a 2 here and a 2 over here. So we're going to start what's known as the molecular equation. So the molecular equation looks very much like what we just drew above, except it's going to show where each of the materials are. So lead nitrate, aqueous, plus 2 Ki, aqueous, reacts to form lead iodide, solid, plus potassium nitrate. So this reaction will also note, because it's producing a solid here, that defines this as a precipitation reaction. Any ionic solid that dissociates, we can tell because it's going to have this AQ after it. And any compound that won't dissociate, that'll stay together, that forms a precipitate, will be denoted by having solid after it. And in a couple of minutes, we'll show how we can determine whether a species is going to be dissociated or not. So the ionic equation is the longest of the three because it's going to show all of the individual ions. So we take what we had on the previous page. So lead nitrate, for example, that fully dissociates. So that becomes lead 2 plus aqueous plus 2 nitrate aqueous. Same thing with the potassium iodide. That fully dissociates. So we can separate those ions. 2K plus aqueous and 2I minus aqueous. So that's our reactant side. On our product side, we saw that the lead iodide doesn't dissociate, it forms a solid. So that stays together. And then the final compound, the potassium nitrate, those ions also would be dissociated. So that's known as our ionic equation. The last one is the net ionic equation. And it comes from some things that we may have already noticed in our ionic equation. And that is this potassium plus is the same on both sides. Same thing for the nitrate ions. Those are the same on both sides. Basically, these are ions that are left unchanged by the reaction. And so we refer to both of these, the nitrate and the potassium, as spectator ions. So the net ionic is just whatever is left over. Because if something is on both sides of the equation, just like with the math equation, we can cancel it out. And so what we're left with now is lead 2 plus aqueous plus our 2 iodide ions react to form lead iodide solid. And so what we need to be able to do is to look at these types of situations, especially if we only know what the starting materials are, and can we predict, you know, two items, will a precipitate form? And if one does, what precipitate forms? So we're going to look at the following table. And this gives us some basic rules to follow. So if we have an ionic compound where the cation is lithium, sodium, potassium, or NH4 plus ammonium, essentially that compound is going to be soluble. And that's regardless of what the anion is. Same thing is true for nitrate as well as C2H3O2 minus. When we have those anions, basically regardless of what the cation is, that compound will be soluble. For things like the halogens, in most cases, ionic compounds with halogens are soluble. However, if they pair with silver or mercury or lead, the compound is generally not soluble. And sulfate is somewhat similar to that. In most cases, sulfates are soluble, but if the sulfate pairs with calcium, strontium, barium, or lead, then it's not soluble. Then below we have some ions that are usually not soluble. Things like hydroxide, sulfide, carbonate, and phosphate. Although we can see in some specific situations Basically what we saw in the table above. So the table above said lithium is pretty much soluble with any anion. And that's what we're seeing down below. Hydroxide is generally insoluble unless it's paired with one of these cations from above. Same thing for carbonate and phosphate. They're generally insoluble, but with one of those 4 ions from above, they'll generally be soluble. So we can use this information with what we're about to do to determine what's going to happen from a possible chemical reaction. Now, these types of reactions, the first one we saw was the lead nitrate with potassium iodide. These are often known as double displacement or metathesis reactions. And they usually take on the form that looks like this. Basically, the cations and anions trade partners. Now, in order for one of these reactions to take place, we need what's known as a driving force. So a driving force is something that will cause this reaction to actually happen. And the 3 things that we're looking for as driving force is the formation of a gas, the formation of a precipitate, or the formation of a weak or non-electrolyte. So let's look at an example or two. So what if we have sodium sulfate, and this is often how you'll see problems like this worded. Sodium sulfate reacting with barium chloride. So let's just start by writing out the equation. So sodium sulfate, Na2SO4 plus barium chloride reacts to form barium sulfate plus sodium chloride. And then we can balance this by putting a 2 in front of sodium chloride. So the first thing we need to know, are all of these compounds soluble? So let's go back to our table. So first one, sodium sulfate. We can see in the bottom row of the top section that sulfate is usually soluble, but there are some exceptions: calcium, strontium, barium, and lead. If we go back to our equation, the first one is sodium. That's not one of our exceptions, so that will be soluble. But barium is one of our exceptions. We just saw that sulfate, when with barium, is not soluble. That forms a precipitate. And then we have barium chloride and sodium chloride. And we can see in the third row, chloride is generally soluble except for silver, mercury, and lead. We have barium and sodium. That's not one of the exceptions. So these will be soluble as well. So that is our molecular equation for this reaction. What's our ionic equation going to look like? Well, that's where we split everything up. And don't forget all these aqueous, because they are an important part of these equations. Barium sulfate, because that's solid, that stays together. And then the sodium and chloride ions of sodium chloride will dissociate as well. So if we notice now, we have spectator ions here in sodium and chlorine. So our net ionic equation is going to be what's left, or what's changing. Barium 2 plus sulfate 2 minus forms barium sulfate as a precipitate. So that's our net ionic equation. What's our driving force? Our driving force is the production of a solid, barium sulfate. All right, let's do another example. Let's say that we had sodium chloride plus potassium sulfate. All right, so sodium chloride, NaCl, plus potassium sulfate, K2SO4, reacts to form potassium chloride plus sodium sulfate. All right, so what is going to be dissolved and what's not? So we've got two chlorides, potassium and sodium. If we look at our third row, chlorides are soluble except for silver, mercury, and lead. Well, we have sodium, so that's aqueous, and we have potassium, also aqueous. Now we have sulfate. Sulfate, you can see in row 4, is soluble except for calcium, strontium, barium, or lead. So that's aqueous as well. All right, so this looks like a different situation than what we've seen before. What happens when we split this up into its ionic equation? So there's our left side. Both species dissociate. We've got 4 ions. And I'll put the product side on this line below. All right, so what happens? So on the left, we've got 2 sodiums. On the right, we have 2 sodiums. On the left, we have 2 chlorines. On the product side, we have 2 chlorines. On the reactant side, we have 2 potassiums. Same thing on the product side. And finally, we have a sulfate and a sulfate. So what happened here? Well, there's no driving force. Recall, our driving forces are the production of a solid, a gas, or a weak or non-electrolyte. We don't have any of those here. And because we don't have any of those, this will result in no reaction taking place. All right, let's do one more example of these. And we'll continue that on the next video.